Okay, thank you, Dr. Zhang.
Thank you very much, Dr. Turner. Thank you for the introduction, and it's really a pleasure to have this opportunity here. And today my topic will be spatial temporal trajectories in resting state FMRI reviewed by convolutional variational autoencoder. So I guess let's say we want to figure out how human brain works. One method to do it is to use functional magnetic resonance imaging, also known as fMRI. And this method allows us to non-invasively measure the time series of whole brain activity, which is very cool. And it's based on the blood oxygenation level dependent signal, also known as the Bose signal. And one way to do this is to acquire data on the resting state, meaning that the subject is not performing any kind of task. And to analyze this kind of data, we usually use Pearson correlation, also known as the functional connectivity. So here is just an example for some background. Basically, we just select two voxels and try to calculate the correlation between the two. And then you can do this for any pairs of voxels. So you end up having a matrix, the functional connectivity matrix that represents how the different brain regions are connected with each other on the resting state. This method does assume a constant relationship between different brain regions over the course of the entire scan, which is not necessarily true. So as you know that recent studies have found temporal variations in functional connectivity. And the most commonly used approach is the sliding window correlation. This is relatively straightforward. You basically just apply a sliding window, and within each window you calculate the functional connectivity. But as you can see that when the window is sliding, you end up having different functional connectivity matrix over time. So it suggests temporal variations. But I mean, sometimes it might be tricky to determine the correct window size. So people also try to figure out if there are any other ways to do this. And there are a couple of approaches like the independent component analysis or the point process analysis and co-activation pattern analysis, and also hidden Markov models. Um, I don't know if I should go to details, but basically, I guess many of the methods like the point process analysis is like selecting a few fMRI frame that has relatively high amplitude that's higher than a predefined threshold, and which is also similar to the concept in co-activation patterns. So basically, you are trying to focusing on these individual fMRI frames. And the hidden Markov model is also something similar, except it tried to figure out how the brain state will transit to another using hidden Markov model. But basically, you can see the idea is that many current approach focusing on these individual fMRI frames, meaning how different brain regions would co-activate with each other at any given time frame. So this essentially creates a discretized brain states that are defined by the spatial configurations of a network activity. And then you may be wondering, in reality, these things might be continuous. And could we actually figure out a way to model the continuous transition of brain activity using some sort of characteristic spatial temporal trajectories? And in the past, in our lab, we have developed a method called quasi-periodic patterns, also known as QPPs. Um, I guess basically this method just it applies an algorithm to figure out these reoccurring spatial temporal patterns For example, here, this particular pattern is happening multiple times along the course of the entire scan. And this pattern itself, it has the default mode network and task positive network, which are two major networks in the brain, showing opposite phase, and it's like an anticorrelated relationship, and it's also roughly a sinusoidal wave over the course of around 20 seconds. So this is very interesting, and I think this is the kind of characteristic spatial temporal pattern that we are looking for. And you can actually obtain multiple QPPs. For example, in the recent work that Banas did in her, I think, neural image paper, we can perform regression once we obtain the first QPP, so that we can apply the same algorithm again to obtain the subsequent QPPs, like um, like secondary QPPs. But I mean, using that approach, the amount of QPPs you can obtain is it could be limited to a few numbers, like I guess 4 or 5. While there could be more than I mean, just more patterns that could have some significance, but were ignored in the past because their variance explained is relatively small. And we were wondering if we can use deep learning method to obtain this kind of um, this small structure that were previously ignored using deep learning method. Specifically here, we're trying to use a variational autoencoder to perform this task. So that's the I guess the motivation of this work, and um, and here I guess I'll talk about the method part. So the data was downloaded from the Human Connectome project, and what we did is sort of pre-processing that contains several steps. So first, we remove the first 5 frames to minimize the transient effect, and then we perform regression, which involves green matter, white matter, and CSF, as well as the motion parameters and linear and quadratic trends. And after that, we perform bandpass filtering and project everything into a into Brainterm Atlas. So here's a graphical representation. Let's say this figure represents the data we have, the pre-processed volumetric FMRI data. As you can see, it's a 4D vector. You have x, y, z, and time, right? And then we project it into the Brainterm Atlas, which has like 246 parcels that are defined by their anatomical structures. So basically what we did is to I guess just average all the voxels within each parcels to create the signal for that particular parcel, and we end up having a 2D vector, 246 by time, showing the I guess brain state at any given time. And then we reorganize these 246 parcels into 7 different networks using Yao's 7 network atlas. And I guess this is the final result we have. Um, we start from a 4D, sort of a movie of brain activity of FMRI time series. And it's projected into a parcellated FMRI, which is in 2D space, meaning that we can visualize everything using a copy plot. We plot the parcels against time. And if you notice that they're divided into 8 different groups along the y-axis, and they correspond to these regions defined by the Yao 7 networks. For example, the purple one here, it's the visual network. It's located in the back of your brain, and it actually it actually this figure allows you to go back to the original brain space. You can see the visual network actually has like consists several lobes and gyrus. So I think this is a very nice representation. You basically um, it's always easier to visualize everything in 2D instead of 4D. And also it allows you to go back to the original brain space. But in the same time, you can sort of visualize the interactions between or within different networks at any given time. So this is the I guess because of this we use this copy plot as our input data unit for our neural networks. So that's it for the for the FMRI signal preprocessing. And now I will talk about, I guess, some background about the neural networks. So for those of you who are not very familiar with this, um, I guess autoencoder are basically a class of neural network that try to create an identical copy of the input being the output. I guess it might sound trivial, but you typically will enforcing a low dimensionality in the latent layer in the middle, so that you artificially create a bottleneck. And when the data try to pass through this bottleneck, you're essentially forcing the network to learn the most important features in the data. And variational autoencoder is very similar in the concept. Instead, except they try to map into a random distribution instead of a deterministic variable. And this actually will become more robust and make they also made different latent variable orthogonal to each other. So both are very desirable features, which is why
Okay.
we use variational autoencoder in this case. So just a little bit more explaining, I guess neural networks they are essentially a bunch of trainable weights, right? And when you train a neural network, you use gradient descent or back propagation, which has like two steps. In the first step, in the forward pass, you calculate the loss function. And then in the backward pass, you use the loss function to calculate the gradient of the loss with respect to the weights, so that you can use this gradient to update your weights, and you can repeat this like multiple times, and it will gradually converge to some locations. And then the network you end up having, uh, all you try to learn is how to minimize the loss function. So in a way, loss function just defines the behavior of your neural networks. And what makes the variational autoencoder different from a plain autoencoder is also how the loss function is defined, as you will see in the next slides. Um, so the loss function in the variational autoencoder has two parts. The first part is the reconstruction loss, which can be used, I guess, mean square error. So by minimizing this loss function, you are essentially making the output identical to the input. So this loss function is the same as the one you will see in a plain autoencoder. Now, what makes a variation autoencoder different is the second part of the loss function. It's a KL divergence that models the random drawing process. So I guess KL divergence, you can think of it as a measurement between two random distribution, like how different they are. And then I won't go into detail about the equations, but basically it's hard to calculate. But if you make like two specific assumptions here, like the first one being the latent variable distribution follows a Gaussian distribution, and you know its mean and variance, they are both estimated by your network. And then the second assumption is that the reference distribution is a standard Gaussian distribution. Now the reference distribution is sort of the ideal distribution you want your latent variable to try to follow. And if you make these two assumptions, then you can calculate the loss function using a closed form, meaning everything can be actually calculated. And I guess minimizing this KL divergence just push your latent variable distribution towards the prior distribution. And that's because the KL divergence measures the difference between the two, right? So if you are minimizing the difference, then you are essentially making them the same. So now you can train both loss functions combined, and that will give you a variational autoencoder. I guess, is that making sense? Um, if everyone is good with this, I can just continue, but
We
I
don't have any questions in the chat window. I don't know if anybody has a question that they'd like to ask right now. We can take a second. You can just speak up and ask. I rather like this because I was used to the autoencoder that tries to recreate the original signal, but I wasn't familiar with the variational autoencoder, which tries to sort of get this distribution of errors to be the same, not just the overall error. Is that the idea?
Yeah, kind of. I guess I have a more one more slide to show
Okay.
an example. Yeah, that might answer your question. So let's see. So you now know the theory. Now, the idea is that we can use a simple model. I guess simple example. Try to project a 2D image of handwritten digit, try to project into some kind of 2D latent space using variational autoencoder. Now, if we train it using only the mean square arrow, meaning only the reconstruction arrow, then you're basically doing it with a plain autoencoder. So basically a variational autoencoder without the KL divergence part is almost identical to an autoencoder. And this is what you will end up having. You have this sort of a latent space where different locations represent different digits, and it sort of show different clusters, right? But you can see that there are some gaps between different clusters that you don't know how to interpret. So the latent space is not smooth in a way. And then if you train it using only the KL divergence, then everything becomes like perfectly Gaussian distributed. But this time, none of the digit can be like it can be differentiated because like everything is mixed together, and this is not ideal. But if you train it with both loss function combined, then you kind of have a mixed effect of the two. You not only have this kind of distinct clusters for each class, I guess, or each handwritten digit, but in the same time, the overall distribution of the latent space is still roughly Gaussian, as you can see here, and meaning that it creates a smoother latent space, and you have a better interpretation of every single location of the latent space. And also, if you remember, it's a standard Gaussian distribution, meaning if we have like multiple variables, then each pair of latent variable are kind of orthogonal to each other. Because for a standard Gaussian distribution, I guess they are uncorrelated by their prior assumptions. So you essentially can disentangle different latent variable, which I think is very cool. So this has been proved to work for a handwritten digit dataset. And the idea is that we want to try it using our brain activity as well, and try to somehow map the brain dynamic into some kind of high dimensional space where different different location of latent space will be corresponding to some kind of characteristic spatial temporal patterns. So here is the I guess the actual network architecture that we used. So we trained a convolutional beta VAE, and the input data is actually a short segment of FMI signal, I guess. Um, this segment has 24 seconds long, and it was passing through 3 convolutional kernels and 2 convolutional layers, and then 2 fully connected layers, and then it got mapped into a single 32 um, latent variable vector, and this vector got passing through a symmetric decoder so that it ended up being a reconstruction of the original FMI segment. And the reason why we use convolutional kernel here is try to just model the temporal dynamics, because we are applying a 1D convolutional kernel to the time axis. And I guess it's more robust than the fully connected layer, and it's also I guess easier to train compared to a recurrent neural network. Not necessarily outperform recurrent neural network, but in a way it's easier to train. So that's the one we start with. Um, and also it's beta VAE, meaning that the loss function is a weighted sum of the mean square error and the KL divergence. The KL divergence has a heavier weight in beta VAE, and that will give you, I guess, a sort of a stronger regularization effect, so that, as you can see, the latent space becomes smoother, and also different latent variables become more orthogonal to each other. So I think that's both very desirable features, but you cannot just go too crazy about that, and you will end up having a like um, it's sort of a trade-off. So yeah.
Xiaodi, this is Behnaz. I have a question, quick question here.
Okay.
Can you comment on how come is that these 33 time points initially would be, downsized or dimensionality reduced to 17, 9, 6? Do you have any, comment on how come the behavior is in this way? I mean, I have an understanding of how come the parcels can be downsized to less and less dimensions, because we would have networks and such. But it's just, I mean, how come the algorithm behaves in a way that first we have 17 time points, 9, 6.
I see. Okay, yeah. So I guess so I guess a little bit background about convolutional layers or neural networks in general. So the idea is that the data itself, it might be redundant, meaning that something might be correlated with each other. So you don't necessarily need a large dimensionality to represent the data. And the neural network is sort of a learnable ways, and you just provided an architecture, and typically it will start with a very large matrix, but then it will gradually shrink. But as you go into deeper in the layer, and then the deeper layers, it sort of has a smaller amount of numbers, but they represent much more, I guess, rich information. And let's see.
Right. For
Exactly.
example, particularly I meant, for example, what I have in mind is that if we can somehow visualize, that I have very minimal knowledge of autoencoders or deep learning and all that. For example, but I'm just assuming if we can visualize these 6 time points after usage of how many layers? 3, 1, 2, 3 layers. For example, would we see a sinusoidal wave, but in a downsampled time, like 0, 1, 0, -1, 0, for example, right? Do you, I mean, just that's what, so in general, what I'm asking is that when we down size to 6 time point at time course that was 33 to 6, would it be just only down sampling in time, or
No,
you
no,
don't have a good estimate of it?
it's not like a simple downsampling. It's more like extracting more complicated features here. But I mean, there are ways to, you know, visualize these intermediate layers output.
Right.
But
That.
I mean, here I'm not implementing this. So what I only know is what the latent variable would look like. We visualize the final output here. But I guess I can give a sort of an example in another in another example. For example, if you know, if you train a neural network, try to classify different images, like not FMRI, but just 2D plane images, right? And then uh, before you start, everything is represented by pixels, right? You have
Right.
like a huge amount of pixels with intensities. But when you're passing through the first layer, which typically will extract the edges, like different edges at different orientations, and that's sort of a, I guess, a high
So
level
actually, that
down.
is what I'm saying. I'm saying that I have a good, I can have a feel of when you downsample in a space, right? How would you get the spatial features? What you just said as a handwriting, I won't have any time points. I just have one dimension that is all the spatial dimension that can be really down dimensionally reduced to a limited number of dimensions.
Yeah.
Do you get what? So what I don't have a feel of, and I'm just guessing, is that when we down dimensionality reduce the time dimensions, would we get like a time course or something that is like especially like temporally downsampled, or it's not as mentioned, as you mentioned, it's not as straightforward, or you don't have a good answer?
It's not a simple sampling.
Right.
It's like the spatial information, all the temporal information is actually already encoded into the features, and that feature itself can have also, it can also be sliding along either time or I guess space. And then so that's the reason why I bring up the example about the edge. So let's say an edge can be like multiple pixels, right? And then you can have multiple edges, but edge is like an like it's a simple representation compared to, you know, including all the pixels. So in a way, the amount of edge you need would be much smaller than the amount of pixels you will need to represent the same figure. And I guess similarly here, the original FMRI time course can have, like, you know, multiple parcels and multiple time points. But as you go deeper and deeper in the network, each point can actually represent some kind of spatial and temporal patterns itself. And that features can also be varying along time or space domain, but, you know, the amount is typically less than the original one you would need in, I guess, the original input domain, if that
Right.
make any
Right.
sense.
Thank you. Thank you. This was actually great, and perhaps at a point I would reach you directly to ask some
Sure.
further questions. But also, just the second question here to clarify that you flattened the 64 by 6 latent or intermediate latent variable. This flattening is it mostly inspired by the QPP method, or is it something that is a common practice in autoencoder?
It's very common in neural network. Basically, after convolution, you have a high dimensional vector. You just flatten it to a single vector because I guess the following fully connected layer can only accept I guess a single vector. So that's why we apply flatten here.
Yeah, right. Thank you.
You're welcome. Let's see. Okay. Yeah, so we actually we actually tested a few different network architectures. So this is one that I just show you earlier. This is an encoder and this is a symmetric decoder. And we compare it with like two different network architecture. This one is narrower and this one is wider, meaning that the number of latent variables is different. And similarly, we can have a shallower model and a deeper model. So we essentially have 5 different models, and we train them all together to see which one has the best performance. And then for each subject, we have around like 1200 time points. So the way we prepare our data is to apply a sliding window that has like 50% overlapping. So each subject gives you around 73 segments. And then we have 412 subjects that were randomly divided into training set, validation set, and testing set. And we just trained with like pretty standard parameters. And this is the validation loss we got. So as you can tell, two of them seem to be perform pretty badly, I guess, but 3 of them has like comparable validation loss. So we end up choosing model 2, not only based on the validation loss itself, but also we take account into we also evaluate some kind of features in the latent space to make that decision. But I mean I can come to that later if I actually have time in the end. So let's just say we have like trained our neural network. How do we visualize the latent space? Now if we go back to the previous example, we can visualize the handwritten digit. Using this technique, we can create a Cartesian sampling of the latent space and passing these samples through the decoder to see what the reconstructed output would look like and overlay them on top of the latent space so that you can see different locations of a latent space represent different digits. And it sort of like evolving continuously along any directions. So this is a technique that we will use. But here for the brain data, we have like 32 latent variables. And try to project into a 32 latent distribution is just, it's hard to imagine what the figure will look like. So to overcome this problem, we try to, visualize only one at a time. So formally for each latent variable, we change its value from -3 to +3. This is because most of the samples for Gaussian distribution lies in this range, right? And then when we slide in the latent variable along this range, we see what the reconstructed FMI segment would look like. So this would give us a 3D vector. You have latent axis, the spatial axis, as well as the time axis. So essentially you have a 3D vector, and you can visualize this if you I guess making one of them fixed so that you end up having a 2D vector, which is what we are going to do in the next for the result session. So here I'm showing you the I'm fixing the latent variable axis at its maximum. So essentially, I'm showing you how the spatial temporal trajectories in the original FMRI space will look like. The x-axis is time, and the y-axis is the different location of the brain in the 7 different networks. I don't know if we can actually see the labels or not, but from the very top is the default mode network, and then frontal parietal and goes all the way to somatomotor and visual network. And I guess this figure just shows you what kind of spatial temporal trajectories that would sort of produce the maximum amount of activations for a particular latent variable. And each figure represents a single latent variable, and in total you have 32 latent variables. And it's probably a lot of information here, but if you're only focusing on this a specific time point, for example here, the time point here is showing you when it reached the maximum variance along spatial domain. And this figure can be better seen in the second figure, where we just fixing the time axis at the max variance time that I just described earlier. And then, so this time I'm showing you how the latent space samples varies. I'm sorry, how the spatial profile will change along the latent space. So this time the x-axis showing you the latent variable, whereas the y-axis showing you different locations of the brain. And here it can be better seen that the first row, I guess the 6 different latent variables seem to have a very similar spatial profile. And you can actually show the spatial similarity among these spatial profiles, which can, well, I guess you can see there are like 6 different groups, which is why we perform k-means clustering. I'm sort of trying to show everything in reverse order. Like the result I'm showing you is already k-means clustered, but here is why I perform k-means clustering, if that makes any sense. But on top of this, the latent variable were sorted in with their variance explained in descending order, meaning that the one in the front has a much higher variance compared to the one in the back. And if you prefer this way, we can use the average functional connectivity to represent the brain state for each cluster. For example, the first cluster is showing you the anti-correlation between the default mode network and the task positive network. And then the other clusters are showing you something different. But among them, the second one seemed to be, I guess, particularly interesting. This checkerboard look like patterns. It actually matches with the findings in the principal functional connectivity gradient. So in that paper, it was described that our human brain is organized into like, I guess, functional connectivity gradient. You have like multiple gradient, but basically along the first gradient, you start from the higher cognitive center like default mode networks to these peripheries like sensory regions, for example, somatomotor or visual network. And then along the second axis, you have a visual network, or I guess dorsal attention on one end and somatomotor and ventral attention on the other end. And here in our case, the functional connectivity in the cluster 1 and cluster 2 seem to match with the patterns seen in functional connectivity gradient quite well. And I mean, these two methods are quite different from each other, but the results seem to be kind of in agreement with each other. So I think this might actually suggest our brain works this way. But who knows? I mean, I find it very interesting. So and then what else? Oh yeah. So on top of this, our method offers temporal dynamics for these latent variables as well. So if you want to focusing on the temporal dynamics, you can fix the spatial axis, right? So let's say we take an RI and somatomotor region, so that we can show you how the temporal dynamics change along the latent axis. Now on the x-axis is the time, and the y-axis is the it's like sliding the latent variable from negative to positive. And then you can see the first latent variable is showing you some kind of low frequency oscillations that you would see in I guess the primary QBP. But for those in the back, you see this, you start to see very high frequency oscillations that were I guess that didn't receive like too much attention in the past, because mostly because the variance they explain is relatively smaller compared to the primary ones. So essentially, if you just ignore them, the original data set wouldn't be like too different. But I mean, they're still there, so it could be an interesting thing to investigate in the future. And I guess this is just to show our method can obtain like multiple temporal dynamics. And although we haven't really figured out what the interpretation of this high frequency fluctuation is, so yeah. And at the very end, I guess I also want to show you the reconstruction of FMRI segments, because that's what autoencoders are trying to do. They just basically try to figure out a reconstruction. And I think it's very nice because you basically know how much information is lost during this process by comparing the reconstruction with the original. And as you can see, they're fairly similar to each other. And I want to mention that this is the entire FMI scan, but for the autoencoder, we take this short window of FMI segment as our input, which has like 246 parcels and 33 time points. And all of the information here were encoded into a single vector that has like only 32 latent variables. So I think it's a relatively aggressive downsampling in some sort, but in the same time remains it still has a fairly good quality. So I think in a way we can claim that we have found some sort of building blocks of brain state dynamics, because just choosing different weights of these latent variables can produce, virtually any kind of spatial temporal information you will see in an FMI data set. At least for this test, for this training set. I'm sorry, is this training set? No, I think this is actually testing set. So yeah. But I mean, we still need to validate that, and there are some future directions we need to go. So just to conclude, here we propose a new variational autoencoder. We obtain a set of characteristic spatiotemporal patterns. The numbers are relatively small compared to the original data size, and they are approximately orthogonal to each other, so that it kind of help with our interpretations. And then this method captures the most prominent features in resting state FMI, and they sorted in the descending order so that you can choose a shallower model, basically like cutting it off with a lower threshold. But anyway, I guess it kind of provide insight into how like activity flows across the brain, but in the same time, it's also in agreement with previous findings like the functional connectivity gradients. So there are some future works we might be able to do, like try to apply the same method for the task performing versus resting state, so that I guess we can sort of, we would expect some kind of difference, and we can verify that if we actually see this with our approach. And similarly, we can also compare some kind of neurological disease with healthy controls. And if you're interested, our preprint is available in bioRxiv. And with that, I would like to first thank my advisor, the Xiaodi Zhang, for her support. And I also want to thank my CC committee member, the Candice Felicia, Eric Schumacher, John Oshinsky, and Michael Boric. And also, I would like to thank everyone in Calhoun's Mind Lab. And thank you very much for your attention, and thank you for giving me this opportunity to present my work. I really appreciate it. And yeah, thank you.
Marvelous. Thank you so much. I know it's very challenging to present with no audience feedback, and no ability to see whether people are nodding or shaking their heads. But this was very, very interesting presentation. I think we've got, certainly have some time for questions from the audience. Please just unmute and ask.
So I had a question about the autoencoder. So I'm roughly familiar with the general idea of autoencoders, but I guess I didn't quite understand what made this one specifically different. Is it the application of like a convolutional network that I'm missing, or well, it's a convolutional beta autoencoder. So I guess what does the convolutional beta mean?
Ah, I see. Okay. Let me see if I can go back. Oops. This slides. Okay. So yeah, it has several parts. Like, so I guess for normal variation autoencoder, you probably just have a bunch of fully connected layer, and also map to a latent variable distribution, right?
Right.
And you can use convolutional kernels to replace some of the fully connected layers. So the idea is that we apply the 1D convolutional kernel to the time axis. So essentially, we are trying to let the convolutional kernel to figure out the temporal dynamics. And I guess compared to a fully connected layer, the convolutional kernel has parameter sharing, right? So that it has fewer parameters, and in a way, having fewer parameters would make it more robust, since it's a sort of a regularization. And that's why we apply convolutional kernel here. And for the beta VAE part, so beta is like a weighting factor for the KL divergence. If you choose a beta equal to 1, then it's a plain, it's a normal
Right. Okay. Yeah.
variation autoencoder. But beta is like, I'm like, I value the KL divergence more than the actual reconstruction quality. So
Mm.
at the end of the day, it's like I want the latent variable to become more orthogonal to each other. Oh, right. I have one more figure to show if I have time. Let's see. Okay, can you see now? So we actually compare it with the plain autoencoder, which has beta equal to 1. And here is the beta equal to 4. I'm showing you the, let's see, the correlation among spatial pattern. It's basically the spatial similarity. And it and in this case it's almost an identical matrix, right? We have the diagonal element equal to 1 and everything else is close to 0, meaning that the features extracted are orthogonal to each other. They are not correlated. But in the plain out in the plain variation autoencoder, it's still better than an autoencoder, but I mean, in terms of the correlation between different latent variables, it's not as good as the beta VAE. So since are just correlated with each other, and I guess just try to disentangle everything just makes interpretation easier, although the actual reconstruction quality is fairly similar.
Okay.
If that makes any sense. Yeah.
Yeah. Thank you.
Thanks for the question. It's a really good one.
Other questions, either about the technique or the application? I actually had a question, because it wasn't clear to, I mean, I think it's actually really interesting to see the resting state reconstruction at the end. And I think what you found out about the gradients of connectivity and how those cluster together could be really interesting. Is there, at what point would you start extracting features from an individual that you might be able to correlate with individual characteristics? It's like if you said, okay, what in this is actually related to working memory capacity or language capacity or something, you know, how does it reflect behavior? How do you have a sense of how that would happen?
Yeah, that's a good question. I I really haven't, think about this far. And let's see. The the reconstruction I showed earlier is actually based on each subject. But for that particular pattern you were talking about, that were compared to the principal functional connectivity gradient, that one is actually an group average. So
Okay.
I guess, yeah, at the end of the day, we want to go toward that direction, but I guess for now, I don't really have that kind of plan yet.
Well, we can chat more later, I'm sure, about how
Sure.
that might work.
Okay.
Excellent.
This is Behnaz again. I think related to what Dr. Turner said. I know that people who work on functional connectivity gradients have done recent massive work on relation to behavior or mostly behavior rather than task interactions. And they have, some of them have pretty impressive results, particularly the ones that, for example, I mean, the most impressive is on the striatum and the gradients that the striatum has with relation to impulsive behavior and such. But I know it's, I mean, their work is based on a static map of functional gradients, either in the cortex or in the subcortical, particular subcortical region. But I think what methods like Xiaodi or the QPP method has is nuanced timing information. And that can or cannot, add more, power or significance to correlation with behavior or not. This is a very, an area of research that is worthwhile, worth pursuing, as you suggested. And I know Shella and everybody in Dr. Eric Schumacher, everybody in the community, in the committee are supportive of that. Actually, I haven't had a chance to talk with Xiaodi and Shella about this work, but one thing that is the fact that Xiaodi started by these 33 time points, which is roughly equivalent to 20 seconds. And the new method that I'm working on suggests that this 20 seconds that is very much biased by the QPP algorithm. And it's actually equivalent to the center frequency, which is 0.05 of the common FMRI band. And what I, for example, see in my method, in the new method, is that if we start by 33 time points, we get patterns that are 33 time points long with one cycle of activation, deactivation, one cycle, or we get faster items that Xiaodi showed is probably because he started with 33. Like if you start with 30 time points, say, you get a cycle of activation, deactivation that is last 30 time points, and then you get a shorter cycle, which is like 15 time points, exactly half of that.
I see.
And it could make sense. I remember even with this QPP method, Mikhail Beloy, who has worked on this, changing the window length for the QPP method, we had this observation that whatever window length we set, we get a cycle of activation, deactivation. With the new method that I have worked on, developed, it is in the under preparation, suggested by, very much helped by Taylor Bolt, which was the postdoc in our lab. Actually, that answered a very big question that I had from the start, and could answer it, that it is very much dependent on the window length that you start. And I think I just can, based on the new method, I can just hypothesize if Xiaodi starts with different window length, he gets a cycle of activation, deactivation, and that actually shows this the scaleless nature and all that. Right now, I think I just wanted to say that this 20 seconds is actually one of those key points in the algorithm. One of those key points that is biased by the previous algorithm, and there is a room to improve that with Xiaodi's method. I have in my to-do list to get to Xiaodi directly and discuss a few of the points that I have learned working with QPP throughout some years, and share it with Xiaodi so that he can examine this with his new method.
Yeah,
It's
a very good point. I think, yeah, it's definitely very interesting to see if my result would be any different if I change the window length. Yeah,
also a very minor point that when you see like your third gradient on, when it started to not exactly match the third gradient on Margulis, which like I got, that was where we are diverging. And my guess is that when I looked at the result that you show now, and also in the manuscript, it might be that because you are including subcortical regions. In the third, for example, your third latent variable, if you can bring it up, you had this correlation of subcortical with ventral attention, and I think somatomotor or other networks. So it might be that even the divergence, if you only include cortical areas, you would have, yes, more matching of your more matching of latent variables. See, cluster 3, you have a strong coactivity of subcortical with ventral attention and kind of somatomotor. But this like participation of subcortical is very strong in my opinion. And Margulis' work is mostly, the 2016 published work is based on cortical areas. So that might be that might be the reason that your cluster 3, for example, doesn't match Margulis's third gradient, or QPP 3, for example, or 2, whatever we get.
Yeah, that's an important point. I do want to be mindful of everybody's time, because I know we usually end right at 3, but I do really enjoy this conversation. So I wanted to let the folks who I know in my lab need to head out at 3 o'clock to go ahead, and I'm going to stop the recording, but we can certainly stick around for a little bit longer if we want to keep chatting.